Next model is about megafaunal extinction, and I'm going to do it in 2 steps, 2 videos. So in this one, by contrast to the previous one, we're assuming that the humans, they kind of show up, and it's now not a fixed area of land that they're exploiting. It's a population of animals, which implicitly the animals are living on a fixed area of land. So they have their reproduction function, which is depending on the land and so on, and the characteristics of that animal species. Okay. So the humans, they show up, and there's a bunch of animals out there, and then the question is, what happens to the human population and what happens to the animal population? And we're kind of thinking that the whole thing happens over a relatively short time span, like a few hundred years or even less. So we can just hold the human technologies constant. We don't need to worry about technological change. Okay, so in a way, this model is simpler, or at least the model of the human population is simpler because we don't have to worry about technological change, but what we do have to worry about is the change in what would have been in the previous model, the land area R, but now it's not the land area R, it's the number of animals N, which the humans are living on. Okay. So, what's the model? We've got, again, oh yes, I need to do some rubbing off, sorry. Okay, so again, we've got production Y. But now we're saying production Y is just harvest. So how much can you harvest? Well, it depends on how many harvesters there are. L, the labor force, the number of people. Okay. But it also depends on the number of animals. So the idea here is the humans are going out there searching for animals and killing them and bringing them back with a certain fixed technology. So if you double the number of humans for a given number of animals, they'll find twice as many in a given time. Double the number of animals for a given number of humans, again, we assume that the humans will find twice as many a given time. Okay, and then there's a productivity factor, which we now just call phi, rather than some kind of AL or whatever. We could have said AL actually, but anyway, it's constant, so we just call it phi. Okay, and then what happens to the human population? It's basically the same as before, but confusingly, we're changing notation. So we still have this theta, or theta L. Yeah, we call it theta N L because we got a theta N coming later. Theta L, L times something, which is going to be either, well, which can take any value. When it's naught, there's no change in population. If it's bigger than naught, population's growing, etc. And again, it's a similar kind of pattern. It's 1 minus something. But now we set this up slightly differently, and it's y bar over yt over lt. So I'm not going to go into exactly the differences with the previous one. It more or less comes to the same thing. But what we've got here, this is the food that somebody needs to survive, and this is how much they're actually getting, isn't it? Per person. So again, if what you're getting is more than what you need to survive, then this is less than 1, and the population will grow. If what you're getting is less than what you need to survive and reproduce, this is bigger than 1, this is negative, population will fall. Okay, so it's basically the same as before. And then we can use this to say, but y over L is just phi times n. So why don't we just wipe this and say phi n t, and then we've linked the change in the human population to the animal population. But now we want to link the change in the animal population to the rate of harvest. Okay, and to do that we need another logistic, or we choose anyway, another logistic function, nt plus 1 minus nt, so this is the change in the number of animals, is theta n nt times 1 minus nt over n star. So now we've gone back to the classic logistic way of setting this up. So n star is the carrying capacity of the environment for these animals. Nt is the actual number. If nt is less than n star, the numbers will be going up, and so on. But then we need to add something to this, or perhaps you could say subtract, because another thing affecting nt plus 1 is going to be harvest in period t, which we got here, right? You can put t's on these. Okie doke. And this is basically our model we kind of done. Because that basically has knocked it on the head. We've sorted it. Because imagine you've got some initial situation, you know the parameters of the model, theta L, theta N, y bar, phi, n star. You also know the initial situation, the initial number of humans, and the initial number of animals. Then you can stick that in and get the next period number of humans and the next period number of animals, which you can then stick back into the right hand side of the next period equations and get t plus 2 here, and so on. So you can derive like the evolution of the economy. So what's going to happen? Well, let's assume that a small number of humans have shown up and there's loads of animals. Okay, so this could be North America, it could be New Zealand, it could be all sorts of other places. Okay, the humans show up in small numbers and wow, it's like Christmas. What happens? So n is initially large, which means this is small. 1 minus this is quite close to 1, which means you have rapid population growth, close to the maximum possible, which is theta L percent kind of per year. Okay, L is initially pretty small, and when L was 0, n was going to be equal to n star, isn't it? Because there's no disturbance. So n, when the humans show up, n is equal to n star. Then they show up, but this is pretty small. There's not many of them. Not a lot happens initially. But remember, the human population is growing really fast. So before long, this gets big. What happens when this gets big? We've got a big minus term here. So this whole thing gets negative and the animal population starts falling steeply. Okay. Initially it was stable. As soon as the humans show up, it's going to start falling slowly, but before long, it's going to nosedive. But when the animal population nosedives, the human population has risen, what is going to happen next? Oh, this is small, this is going to get big, this is going to go negative, the human population is going to start falling. When the human population starts falling, this gets smaller. Meanwhile, n is a lot less than n star, so this is positive. Before too long, the animal population is going to be able to recover, and so on. So you get these cycles. This is a classic sort of predator-prey cycle, which you can see. I don't know if you can see it on this video, but you can see it in the book or in the lecture notes. So the animal population is not driven to extinction. Why not? Well, the humans are dependent on the animal population. So when they start knocking it way back, the humans will start dying as well, and so the animal population can recover. Okay. So in a way, it's a kind of optimistic conclusion, but we'll talk a lot more about that while in the lectures. But stuff we really depend on, we don't tend to wipe out, according to this model anyway. I'm just going to pause that for a minute. Okay, so could the humans do better than this? So in this model, they just go out and hunt for all they're worth, whatever happens. And if there's loads of animals, they kill loads of animals, and their population goes up. But then they have these crashes and so on. Is that really optimal? Probably not. We're not going to look at optimality here. That's a complex dynamic problem. But we're just going to think about, imagine if they had a zero discount rate and they just wanted to maximize their stable population. How would they? How big a population could they have, and what hunting rule could they have to achieve that? So, if we assume that the population is stable, then that has to be naught. But if it's all stable, that means that the animal population has to be constant as well, otherwise it's never going to be stable, is it? And if this is naught, then this has to be 1 has to equal this, so we get y bar is equal to phi times nt. That must hold in a stable situation. But it must also be the case that phi lt nt is equal to this. These must be also equal, right? So phi nt must be this divided by lt, which is theta m nt over lt 1 minus nt over n star. Okay, so this must hold on the sort of what we could call a steady state, a situation where both populations are stable. So this has to hold on a steady state, but what is the best steady state? Well, if we're calling the best steady state the one with the biggest human population, let's rearrange this and say that LT, bringing that up, is theta n over y bar, bringing that down, times nt 1 minus nt over n star. So we've got this relationship between LT and NT, and we want to find the NT that gives the biggest LT. How do we do that? Yeah, we take a first order condition, don't we? So we say that the LT by the NT should be naught. And we're going to differentiate like economists and say that LT is this. So we differentiate this one, we get just LT over NT. Yeah? When we just differentiate on here. When we differentiate on here, we get LT over 1 minus nt over n star, and then we go inside and we get minus 1 over n star. Minus that equals 0. We can shift that over and we get that. So we can cancel out the LT's, and we've got that. And pretty quickly we can simplify that to get that nt is n star over 2, which makes a hell of a lot of sense, because that's what we call the maximum sustainable yield. Or when the population of animals is half of the carrying capacity, that's when their reproduction, the rate of reproduction is as high as it can be, which means that the rate of harvest is also as high as it can be, sustainably. And if we stick this back into here, we get the maximum sustainable human population, which is theta n over y bar times n star over 2, 1 minus n star over 2 over n star, blah, blah, blah. It's a half, so it's n star over 4. So we call that like L double star or something. The optimal population, or the maximum long-run population, is this. So the bigger is theta n, the bigger the human sustainable population is. That's the faster animals can reproduce. The bigger n star, the bigger the animal carrying capacity, the better, the less humans need to eat, the more there can be. Okay, that is the end